Hey guys, welcome back for our last set of notes over chapter 17, Entropy, Free Energy, and Equilibrium. We left off last time with this idea that spontaneous processes had a delta S that was positive, which meant that we were increasing the entropy of the universe. And then processes that existed in an equilibrium had a delta S equal to 0. So because they were reversible reactions in an equilibrium, they weren't really increasing the disorder of the universe. So if we keep things at a constant temperature, we get this equation for Gibbs free energy, which is delta G, the change in Gibbs free energy, is equal to delta H minus T delta S. One thing to note when you use this formula, it is very useful. Temperature is in Kelvin, and delta H and delta S have slightly different units. Delta H is kilojoules per mole, and delta S is joules per mole. Now there's 1,000 joules in a kilojoule, so you will want to convert to make sure that these units are the same. And since delta G is in kilojoules, we'll want them to both be in kilojoules. So that's Gibbs free energy's equation. If your delta G for a reaction is negative, that means the reaction is spontaneous in the forward direction, so it's energetically favorable. If your delta G is positive, the reaction is non-spontaneous, but of course the reverse reaction would be spontaneous. And then if your delta G is equal to 0, which is pretty rare for most of our calculations, then our equation would be perfectly at equilibrium. So delta G naught of a reaction is standard free energy of a reaction. It's the energy change for a reaction if it occurs under standard state conditions. And that's pretty much just what we're using for our calculations. And so we do this the same way, products minus reactants, where the coefficients of each individual chemical are used, multiplied by the value for delta G naught, because delta G naught is kilojoules per mole. So then here's the equation you're more familiar with, which is the moles times the delta G of all of our products minus the moles of all the delta G of our reactants. So standard free energy of formation is our delta GF. It's the free energy change that occurs when 1 mole of a compound is formed from its elements in standard states. Really all that means is it's the delta G values from your textbook, which I think is Appendix 3. Any element in its stable form is 0. It's not uncommon for you to see, look up some delta G's and of solids or gases and find that a few of them have a 0. Okay, so here's how you'd solve this. You'd find free energy change, delta G, following reaction at 25 degrees Celsius. You go to that table in Appendix 3. You find your products minus your reactants. So it's 12 times the value of carbon dioxide plus 6 times the delta G for water. Make sure it's liquid water. There are different waters. Minus 2 times the delta G of C6H6, which would be benzene. And then 15 times O2, and O2 is one of those that's worth 0. So you could write plus 15 times 0, but it's not going to change your math. And when you're all done, you find that it's negative 6,405 kilojoules. So it's very, very negative. So reacting benzene with oxygen to make carbon dioxide and water is very spontaneous. It's energetically favorable to do that. So our answer would be yes, absolutely it is. Okay, so here's the relationship between delta H and delta S. If both are positive, the reaction proceeds spontaneously at high temperatures. If delta H is positive and delta S is negative, then your delta G will always be positive. If delta H is negative and delta S is positive, your delta G is always negative. And if they're both negative, it proceeds spontaneously at low temperatures. So really it's the T that can mess with these reactions. So here's spontaneity of chemical reactions. The pressure of carbon dioxide tells us how much product we're forming, and as we increase the temperature, we're really not decomposing calcium carbonate much at all. And then once we get above about that 800 mark, we get a very, very, very high pressure of carbon dioxide, because we know that at the temperature of 835, we become spontaneous. We start to produce a lot of carbon dioxide because we're favoring products. So there's its delta H is positive, its delta S is positive, and we need to get to the temperature of 835 to make this delta G negative. So hopefully that kind of makes sense. So here's delta G at 25 degrees Celsius is positive. When it's 835 degrees Celsius, it's 0. And so if it's 0, any temperature above that will make our delta G negative. So here's phase transitions. If delta G is equal to 0, we're at a dynamic equilibrium. And so we can say that that's equal to delta H minus T delta S. So liquid water going to gaseous water, we can rearrange this. If delta G is 0, we can rearrange just this portion set equal to 0 and find that delta S is equal to enthalpy divided by temperature. And then we can take our enthalpy from the book and our temperature the reaction occurs at, and we can find a delta S of our reaction. So that's kind of a cool trick. Efficiency of heat engines. This is called Carnot efficiency in physics. It's the hot temperature minus the cold temperature divided by the cold temperature times 100. It might remind you of perhaps percent air formula. And basically there's a heat reservoir and a heat sink, and so the heat that we can put to work is good. The cold temperature, that heat that we're losing, is not going to any work. So we look at a little tougher one, which is chemical equilibrium. New formula, delta G is delta G naught plus RT natural log of Q. Q you'll recognize before as a reaction coefficient, and R we've seen before as well. We use the gas constant of 8.314 joules per Kelvin mole. T is temperature in Kelvin. Q is our reaction quotient, which you'll recall is product divided by reactants. So at equilibrium, our G is equal to 0, and our Q should be equal to K, which I remember from a couple chapters ago. And so at equilibrium, 0 would be equal to delta G plus RT natural log of K. And that's how we get this formula here, which is delta G is negative RT natural log K. So you'll use this, and you'll also use this. Here's free energy versus the extent of our reaction. We're going from reactants to products. Q is less than K, so we make more products. Q is equal to K, we're at equilibrium. And if we overshoot equilibrium, Q is greater than K. So that would be more products than reactants. And then here's another graph of pretty much the same thing, except for here delta G is greater than 0. So it's not spontaneous, and so of course you can see that our reactants have a lot higher energy than our products. That's why it's not spontaneous. But our Q less than K, equal to K, and greater than K are the same. So our equation works both for spontaneous and non-spontaneous reactions, which is pretty much what this is showing you. So here's a formula. We'll use this quite a bit. If our K is greater than 1, our natural log of K will be positive, and our delta G will probably be negative, which means our products are favored. If our K is equal to 1, the natural log of that will be 0, which makes our delta G 0, and our products and reactants are pretty much at equilibrium. And if our K is very, very small, the natural log of it will be negative, which will probably make delta G positive, and that means we favor the formation of reactants. So we're applying Gibbs free energy, which was pretty simple, to equilibrium, which was not too bad, and we're determining both free energy at equilibrium and whether or not we're at equilibrium yet. And that's what this formula is really useful for. So here's an example of biological systems. Humans and animals, we take in glucose. We produce carbon dioxide and water as waste. And from that glucose, we take ADP and turn it into ATP. Now this is a chemical reaction. We then consume that ATP to do all sorts of things, one of which is to build amino acids into proteins. It does many jobs, but that's one of them. And in this example is we're taking alanine, which is an amino acid, glycine, which is an amino acid, and we're making them into like a simple peptide, alanoglycine. And to do that requires this ATP. And so the delta G for this is positive 29 kilojoules. So this would not happen on its own, but in order for us to make proteins and stay alive, we have to consume that energy from our ATP. So the K is very, very small there. Here's the whole reaction: energy, water, alanine, glycine, ADP, because we've used the ATP up. And then this is the phosphate, the inorganic phosphate that we lost from the ATP, and then our simple peptide that we've made. And here, when we use ATP, it's now a -2, so it is spontaneous. And our K is much greater than 1. So These guys, without ATP, not going to happen. With ATP, is going to happen. Here's ATP and ADP in their ionized forms. ATP is adenosine triphosphate. They call it triphosphates because PO4 1, PO4 2, PO4 3, and really our energy is found in these bonds between the phosphates. So when we break this bond and we lose that phosphate, we give off a lot of energy. We become adenosine diphosphate. The rest of it looks the same, just two phosphate groups. Later on we can recycle it, hook another phosphate group back to it, and make it energetic again. So here's our last note, which is a little odd. This is the thermodynamics of a rubber band. It's page 801 in your text, and it talks about connecting temperature with disorder and free energy as well. When a rubber band is not stretched out, it's pretty disorderly. And when it's stretched out, the rubber band actually gets hotter. You can feel this if you grab a rubber band and stretch it out, hold it for a couple seconds and feel it with your fingers. The rubber band is very warm, and it's because we're not going to change our enthalpy. We're not going to change our Gibbs. But when we stretch a rubber band, we take it from more disorder to less disorder. So if it becomes less disorderly, these two have to stay the same. The temperature must increase. So a stretched out rubber band is very hot. A relaxed rubber band is very cold. And so knowing this formula and knowing the temperature change from what we can feel with our fingers, we actually learn about the randomness or disorder at the molecular level of rubber. So it's kind of a cool application of a rearranged Gibbs free energy law. So with that is the end of chapter 17. I hope you found this helpful. Thank you.